In this lecture, you will get some of the fundamentals of vision sensors for traffic safety applications and automated vehicles. You will get an overview of sensor types, pros and cons, and a brief introduction to methods for determining range and relative speed of objects in the camera. CCD sensors, or charge-coupled device sensors, have only one separate readout circuit, or electron-to-volt conversion, separate from the individual pixels. The pixels only do the photon-to-electron conversions. In CMOS, or complementary metal oxide semiconductor sensors, each pixel has both the photon-to-electron conversion and the electron-to-voltage conversion. Each individual pixel can also have a multitude of features built in, some that are hard to implement and realize in a separate electron-to-volt converter. In a few following slides, I will describe some aspects of vision sensors and comment on the differences between CCD and CMOS cameras for each. Note that the proportion of the surface area of each pixel that has photon-to-volt conversion in the CMOS is much lower than that of the CCD, which means that it will get fewer photons per pixel. However, this is often solved by adding a layer of micro lenses on top of the chip to gather basically all the light reaching the surface and use it as useful photons. Dynamic range is the ratio between the largest and the smallest value of the light intensity that can be captured by the camera. The lowest value is limited by noise, while the highest level is limited by the saturation of the sensor. Uniformity is another property of vision sensors. For CCD sensors, where only one readout's electronics is used, the uniformity is inherently better than that for CMOS, where small differences in the electronics for each pixel affect the photon-to-volt conversion. However, today's CMOS sensors also have quite good uniformity, despite its earlier issues. In CMOS cameras, it is often possible to already, when communicating with the sensor, request only a subset of the image, as only the subset of the pixels can be told to transmit their information. This can reduce communication requirements. However, more importantly, CMOS sensors can be designed to have specific features built into the electronics of each pixel, tailoring the output to the needs of the application, and reducing the need for external processing. Another issue to be considered when working with vision sensors is blooming, especially when the application is targeting nighttime capture. Looking at the images presented here, I think you're aware of the phenomena. Also for blooming, there is a large difference between CMOS and CCD. For CCD, blooming is often significant, especially for older cameras. This can be seen as the light-to-electron conversion overflow into adjacent pixels, here represented by the balls overflowing into the adjacent pixels. For CMOS, on the other hand, the individual pixels have their own readouts and very little, if any, such overflow. Now to a summary of CMOS versus CCD. In older vision systems, the dynamic range of CCD were much better than that of CMOS sensors. However, as much research and development have been put into CMOS technology, the gap has basically been closed. CCDs are still, typically, somewhat more light sensitive than CMOS. That is, CCD can better handle low light. However, some CMOS sensors are even better and surpass the CCDs on dynamic range. CMOS has a design that has inherent uniformity issues, but the differences is basically negligible in today's technology. Both windowing and per pixel features is possible and advantageous for CMOS, which is typically problematic to implement for CCD-based cameras. However, one aspect really sets the sensor apart, and that is the sensitivity to blooming. CMOS has an inherent protection to blooming, while for CCD, great efforts need to be taken to tackle the blooming issue. The signal-to-noise ratio, or SNR, is highly related to the dynamic range, and although the differences were large previously, today the performance of CMOS and CCD are similar with respect to SNR. Note, however, that it is very much dependent on the individual sensor, both with respect to quality and price. Finally, price. On a component level, the costs should be comparable. On a systems level, CMOS is potentially cheaper for several reasons, not the least that functionality can be added on a pixel level, which may require more processing in the pixels, but you don't need it externally. As you can understand, the benefits of CMOS are significant today, Most, if not all, automotive applications use CMOS sensors today. Now to a few other aspects of vision systems that are on a level above the choice of CCD or CMOS as a sensor chip. Distortion is something the vision system applications typically need to deal with. As soon as something is to be measured, detected, or tracked in an image, it's important that the information in the image is rectified, that, for example, distances are equal when using image processing. To the left, you see two typical types of distortion, barrel distortion and pincushion distortion. To the right, you see an example of a highly distorted photograph. It is primarily the lens of the camera that distorts the image. However, there are established techniques to rectify the distortion. The order of the readout of information from the individual pixels in a vision sensor also affects the way image captures the real world. Here you see an example of a rolling shutter while the camera is moving. That is, the person taking the photo while moving fast to the left, while taking a picture with the camera with a rolling shutter. The pixels are read line by line, starting from the bottom and moving upwards. First, the bottom line is read, then the next line, and so on. As the camera is moving, for example with a vehicle, the time it takes to read out all the lines can be so long that when the lines are captured at the top, the vehicle has moved significantly, creating artifacts that you see in this image. Interlacing, as you see here, is actually not a major problem for production sensors in automotive applications. Such sensors are just not used. However, it is still not uncommon that interlaced cameras are used in laboratory or field data collections. So what is it? Well, the basics of interlacing started in the 1920s, with the aim of minimizing the bandwidth needed to send images or videos wirelessly. By capturing only every other line on an image, and then the other half, the individual half images can be sent separately, lowering the bandwidth requirements. This was adopted wholeheartedly by TV standards NTSC and PAL. That is, cameras recording for NTSC and PAL typically use this technique still. What is the issue then? Well, similar to the rolling shutter, when an object is moving, the two images will not be captured at the same time and seeing the same scene. As you can see with the hand image, which here was moved in front of a PAL camera, the result is jagged edges. The image is a composite of the two separate every other line images, taking some time apart. In the automotive industry, this typically means blurry images. Here, an example of an image of a car wheel. There are techniques to perform so-called de-interlacing. However, if the image is compressed, the jagged edges become blurred, and such techniques are much less effective. The bottom line is, if you can avoid interlace, do it. In addition to the vision sensors I have discussed so far, there are specific techniques and technologies that enables better camera performance nighttime. There are two main types of night vision cameras, near-infrared and far-infrared cameras, or rather, sensor systems. Fundamentally, they work on different parts of the spectrum of electromagnetic waves. A main difference is that the near-infrared is active and the far-infrared is passive. That is, for near-infrared or NIR, there is an active illumination of the scene in front of the vehicle. A main reason to why standard main beams of a car is not sufficient in nighttime is that it's not acceptable to glare oncoming traffic. By instead using light in a frequency that humans do not see, near-infrared, the scene in front of the vehicle can be flooded with light, near-infrared light, basically in the same way that high beams of the car. The near-infrared cameras are then just collecting the photons from the illuminated scene, including any ambient light and other light sources, typically producing a grayscale image. This image can then be used for image processing, object identification, and tracking. In the first version of night vision systems, the image was made available to the driver also. Far-infrared cameras, or FIR, instead measures a quite different frequency spectrum. The FIR camera measures radiant energy. Although it is not precisely heat, that is the best analogy. Hot objects typically show up as white on the image, while colder objects are black, and the colder, the blacker. And it's typically shown as a grayscale image. This table shows some of the differences between the two camera types. Please stop the video and have a look. You will now get an introduction to two methods that can be used to estimate distances to objects using a single camera, so-called monovision. Description will be on a conceptual level. Let's call the two methods object size-based estimates and flat earth-based estimates. Note that there are several other techniques, but they will not be covered here. Imagine following a lead vehicle, the blue box in the image. At any point in time, the object has a size on the camera, in pixels, and the lower part of the vehicle will be a specific number of pixels from, say, the bottom of the image. As the object gets closer, the size will increase and the number of pixels from the bottom of the vehicle to the bottom of the image will be reduced. The latter assumes that the ground is flat, hence the flat earth base name. The distance is proportional to the gap, in pixels, between the object and the lower part of the screen. Now to the size-based method. Here you see the same type of situation as in the previous slide, but from a top view. The box at the bottom is conceptually showing the sensor with the 1 pixel row. At a specific distance, here 10 meters, the car covers a set of pixels, here 4. Now, let's say that the distance doubled to 10 meters. The number of pixels on the image is reduced to 2. Note that this is just a conceptual description. This relationship can be used to estimate the distance. I will now demonstrate a very simple calibration of an equation of distance measurements using the size-based method, assuming a rectified image, among other assumptions. Here we have an object that we know is 2 meters wide, and we know that the distance from the camera to the object is 10 meters. For calibration purposes, we can get the total width of the image in pixels, the width of the image of the object, and we know the width of the real objects. Inserting them into the equation at the top, we can get the k. We can then get the distance to the object at other pixel widths. Here we see an example with 8 pixels. This relationship is not linear. As you see in the graph at the bottom, the closer the object is, the larger the difference is as a function of distance. The further away, however, the smaller the difference. With this few pixels in the image, at 40 meters, the object is only 1 pixel wide, making measurements for longer ranges impossible. And the difference between 20 meters and 40 meters is only 1 pixel, an extremely low resolution in distance. In the previous slides, we assumed that the width of the object was constant, or at least that we know the width. However, let's say that the object in the previous images was a small car. Now consider the object instead being a wide truck. The number of pixels on the image is at 20 meters the same as for a car at 10 meters. We would do a major error in the distance estimation. So you need to estimate the width of the object you're estimating to be able to use this particular method. Again, this was a very basic and conceptual demonstration of the size-based estimation. There are, however, methods that allow for camera distance measurements to be largely insensitive to the size of the object. Here the concept of stereo vision is shown. Another camera is added, and instead of measuring the width in pixels, the offset or disparity of the object in the two cameras are used in the distance estimate. Naturally, the distance between the two cameras will affect the estimate and performance of the estimates, but overall, the disparity will be the same also for different size objects. Finally, I would like to mention a different type of camera. A camera that can provide the distance directly for each pixel. That is, the color and intensity of each pixel is then proportional to the distance. What makes this possible is what can be seen as a combination of near-infrared night vision systems and LiDAR. By illuminating the scene by a projector of near-infrared light, similar to the near-infrared camera solution, but with short pulses of IR light of known duration, the time of flight of the IR light can be measured in each pixel of the CMOS sensor. The details of the technique are not covered here, but at least you know that the technology exists. The main problem with the technique is that it only lends itself to measurements of short distances, an inherent issue with the camera and the measurement type. Thus, for external sensing, it is typically not a main sensor, but for in-vehicle sensing, it may be good. This lecture gave you some basics of camera sensors for use in traffic safety and automated vehicles. Cameras are likely to continue to be a core sensor type for automotive applications, especially given the benefits of price, angular resolution, and the relative ease of object classification in camera images compared to, for example, radar. Main drawbacks are poor range and relative speed estimates.